Hello. So here I'm going to create an FIR filter in this tutorial, and I will use XADC to sample the analog signal, and then I will use also analog discovery 2 of digilent to draw the bode diagram of the filter. Okay, so at the beginning, I create a project and I create a component that will do the filtering. So to be easy at the first, the filtering is just a moving average, so it is very easy. The board that I will use is Basys 3, so the FPGA is RTX 7. So the all of this indicate what FPGA I'm using. Finish. Okay, so here I will create a component for filtering. Okay, so create design, next, create file. So it is called maybe FIR sample. Okay. So at the input, I have data. So first I have a CLK, then I have a data in, which is a bus, say 12 bits, so it will 11 down to 0. Then it will be data out, which is the output of the filter, which is also the same size. And also I have an enable signal which can be used to have a sampling frequency less than the clock frequency. So enable. Okay. Okay, so I have my filter. And here I just a moving average, so of size maybe 8. Okay, so what I will do is to create a shift register for the data for the X. So I have already did something for 4, and then I will do it for so it is enabled. So here's a process that create a shift register for the X, so the delay line for X, for the input signal. So the X0 is the data in, and then you're just trying to delay the input signal, and the size is 8. So X5 receive X4, and X6 receives X5, and X7 receives X6. Sure, you can do it by 4 also. So yes, so I do it. I repeat it just several times. And the signals must be declared here: X3, X4, X5, X6, X7. Okay, X7 here. Okay, once we have all these signals, we must add them up because we are just doing a moving average. So to do that, because there are 8 signals, so there are maybe 3 other bits will add it to the signal, so the output will not be over 12 bits, but 15 bits. So that's why maybe I create a function to extend the sign. So the function I will define here. So sign extend. So the input is the logic vector and the output also. And assume that I know that it is 12 bits. Okay. and I will extend 3 bits because I want to go to from 12 bits to 15 bits. So x11, so it is the extension of x over 15 bits. And here I just do the addition. So for addition, it is not so complicated. I just do some simple things to show the principles. So y that I will define here as a standard logic vector 14 down to 0 is the sum of all of this plus, so maybe I can do also like this. Okay, so 4, 5, 6, and 7. Okay. And what's happening here? Okay, signal y. Okay. Once y is done, so it is the output of the. It's not still output because it is 15 bit, while the output is 12 bits. So the output is called data out, I believe. Yes, data out. So data out. Receive y. I just use the 12 most significant bit, 14 down to 2. Okay, so it is just the 12 bits. And what's happened here? Okay, so yes, it is for addition, so I will add also 2 libraries. Arith, and signed. So I have not here multiplication, but I do just summation. Okay, so I have this, so it means that all the coefficients are divided by 8. So it is sum divided by 8. So it is the moving average. Okay, so this is the component that I will use in my main problem. So on main program. Okay, so the other thing is to test it. So for test it, we need to use the A to D and D to A. So for A to D, for analog to digital converter, I will use the XADC of the FPGA. Okay. You have a tutorial somewhere. I will show you that details how to use that. So to find it, you just type Vahid Meghdadi, and then home page. You go to enseignement, then conception circuit numerique, and then go to resources. You have Basys 3 here, the board, and you have utilization of XADC. And here you have many details about how to create the XADC very simply. So I will use this. Okay, so for that I need a main program to call this component. So plus, create another one. Maybe I call it main. So create file main. Okay. And then we have several ports. So the CLK is the clock. And then I have another thing, button to reset. Sorry, button to reset. The XADC, sorry. And also I have the analog signal, so it is connected to connector A, and the output is to the B, JB. The outputs. Okay, so both of them are set down to 7 down to 0. Okay, so this is my main. So at the beginning I need to create the XADC interface, XADC. Okay. Okay, so according to, you can go really through the web page that I have shown here. Okay, so all the details are here. So I will be using single channel event sampling. Okay, so it means that you create in your design the clock frequency for sampling. Okay, so if we go through this, so we are in the event mode here. We are in the single channel. The RP is okay, and also FIFO okay, reset in okay. So in ADC everything is disabled. In the alarms also everything is disabled. Okay, in single channel I will use which one? The fifth one. So because I have already give something in the pins. Okay, so all of these details are given here, so you can see everything here. So I select box B5 and N5. Okay, and what else? So it is in trigger. Okay, so I think it is okay. DRP events mode, single channel, reset, and everything is disabled. Everything is disabled also, single channel. Okay, so I generate it, and once it's generated I will use the component. Okay, okay, so in the main I need to add this component, so I click here, no, I go to IP source and then the template, because it is VHDL, so I just copy and paste in my main, so it is the XADC, and then I will instantiate it. Go back here and instantiate. Go back in main. Okay, so there are many things that I know what they are, so I will try to put everything connected to that. So data in, there's nothing, so just put 18.0. Address in, it is the same. So data enable in, so it will be at the end of conversion, which is here, end of conversion, it is here. And this input goes to 0, DRDY, okay. Data out is called data out. This is the same as CLK. Reset in, I will connect it to the button that I put it in the, so it is the conversion, WP-in, so it is the input not used, so I put just 0, and this is I called analog P, and this I will call it analog N. Okay, so the channel out, it is the same, so it is end of conversion, and this is not used, open, and the busy out, not used, open. So now everything is connected, and I just need to declare the signals. So signal DAD, the address DADDR in standard logic. So standard logic vector, and the size is 4 down to 0. So it is 5 bits. Where is it? Okay. 4 down to 0. And I can do for all the others. No, as the address is 6 down to 0. Sorry. And I can do that for all the others. So maybe I will just copy and paste. Okay. So okay, you'll see the out 515 conversed. Okay, so this is, I will go through that later. Okay, so this is the alarm out, open also. Okay, so this is the XADC that will give the samples through data out. Okay. Okay, now we are just calling the our filter. So the component is this. Control C, and I go back to the main. The component is here. Okay, this is a component, and this is end component. Okay. Component. Okay. And then I will call it. So maybe here in order to see also. So it is XADC, and it is maybe your FIR sample. FIR sample. Okay, so what is connected to what? So there's a CLK connected to CLK. There's also data in is connected to, I will call it Y. I will see later what I will put as a name. Data out, no, this is data out is Y. So data out is Y, and data in maybe X, so I will see later. And the enable signal is what? So end of conversion something out. Okay, so this is my filter. Okay, so I just prepared the conversion. So maybe the conversion, the frequency of conversion, maybe it is, say, 100 kilohertz. So for that, I need a process to create this frequency. So here is the process that creates my sampling frequency, my sampling signal. So it is in conversed, and you need to define a counter also. So this is the line that was here. So signal count integer range 0 to 999. So to divide the 100 megahertz clock by 1000, so you have 100 kilohertz of the sampling rate. Okay, so this conversion signal is connected here, and as soon as you put it, so data is ready here. The delay is something about 100 clock cycle. So because we divided by 1000 the clock, so you have enough time to receive that. So the out is the signal is 15 down to 0, and maybe the X, I will just receive the X signal. So it is data out, out, because it is write justified. So 15 down to 4. So it is 12-bit write justified. And this X is connected to my filter. So signal X standard logic vector 11 down to 0. Okay, so this X is going to the FPGA. This is the sampling frequency, and the data out is Y. So Y is 12 bits. So I can also define Y here. Okay, so I have the input and output of my sorry. Okay, so this is the so you have the input and output of the filter. So this data out must be connected to the output. So going through the connection of the XADC from the analog signal and the digital signals. So you need to add this line. So we can go to the website that I presented to you to see what is it. And then you are using two analog signal. One is the negative and another one is positive. Okay, I'm not using differential, so it is single-ended input signal, and it is connected, and the output is Y, and the Y, what's it? And the output is JB 8-bit. So I'm using just a simple 8-bit passive digital to analog. So that's why I just receive the Y. And also you must pay attention to the signal and the format of the signal. So the signal is not signed. So that's why so this signal is signed, Y is 12-bit signed, because everything is done here in signed. Okay, so everything is signed. But the digital to analog converter is not signed. So that's why the most significant bit, the MSB, is inversed. Okay, so this is the same as the out, because the XADC will give you the same thing. So I do just the same, not BO out. 15, 14. Okay, so the X now is signed, Y is signed, and JB is unsigned because it's going to the D2A. Okay, so normally everything is okay. I just run the synthesize to detect if there's some errors. If it is not, so okay, so let's see. I have an error, so I will look at if I can see. Okay, so it is some error in my. It is. Mismatch 12-bit, 13-bit. Okay, so somewhere here I have an error about the size of things. So which line? Which is the line? Okay, in 43. Okay. Yeah, okay, so here, so data out is 14 down to 3. Okay, so I redo synthesizes. Okay, so still another one. Okay, so what's that? It's in the main. So what's that? So array index 13 out of range. Okay. Okay, let's see. What's here? So line 115 here. Okay, so it is a problem of still of size. So array index 13 out of range. Okay. So JB is 8-bit, and this is 1 bit here, and so what's that? So JB is declared how? JB set down to 0, so 8-bit here, and 12 down to 6, 7-bit, 8-bit. So what's the problem here? So y, what's that? So y, okay, so y is, okay, so it is not good here. Okay, so y is 12 bits. Okay, so y is 12 bits because y is the output of my filter. So it is 12 bits, so it will be 11, and it is 10 to 4. So it is 6, 7-bit, 10 minus 4, 6, 7, 8. Okay, and synthesize. Okay, so here it's okay. So now we need to create the XADC file. So this is the file, so it is always at the same place. So I will save it in the project. Okay, so maybe I will change its name. Okay, and I will add it to my project constraint. Next, add files. So it is in project 2. This. Okay, finish. Okay, so first the CLK. So if I go back here, the constraint, first the CLK, so uncomment. So the next one is the unlock part, so GA. Okay. The next one is JB. So JB is also uncomment. And the other one is the button, which was for the reset. So the button, maybe this one, the centered button, and there's no C when I define it. Okay, Now everything is good, and I create the bit stream. Okay, so it will take some times. Okay, now we are going to test it. So open hardware manager, okay, and open target auto connect. So here I connected to my PC, the okay. So the Basys 3 board is connected to my PC, and then I will also run okay, so let me okay, let me connect to that. Okay, so it seems to be connected. Okay, so maybe I put something like 1 kilohertz. Okay, so it is 1 kilohertz, and I try to go to 2 kilohertz, 5. So you have something like low pass filter. So okay, so to draw the transfer function, I just add what? So network. Okay, so let us do something. Okay, so I'm going from 1 kilohertz to 15 kilohertz, so it is not bad. And also here maybe so 0 dB here. Okay, so if I connect correctly the signal, so you have the filter. So because it is a moving average with 8 coefficients, you have all over the bound 8 0. So it is 1, 2, 3, 4, and 4 others at the negative part of the spectrum. Okay, so it is good. So we can also play with that in linear if you want. So it is in linear, so maybe 2x. Okay, so it is the filter. Okay. Good luck. Thank you.